The main thing was I had to tighten the little things so it don't move. I'll begin with order prayer. Heavenly Father, we thank you for this day. And I thank you for these students. And I just pray that you be with us, help us to glorify you again, Lord, what we do. In your brother Jesus. Amen.
Amen.
All right, so now is the time in the semester when I give up on Stillwell. So, there's nothing wrong with Stillwell. Stillwell is a great, great book, but I need a book with definitions that are numbered and theorems that are numbered, because I don't have a lot of time. I mean, to properly lecture from Stillwell, I need to read it, prove everything in it, digest it, and then add numbers, and then I would feel like I'm doing a decent job. But obviously, I don't have time for that. Now there is the story to if we shouldn't give up on Stillwell, of course. I mean, we should definitely read his discussions as we think about the totality of this subject, because his discussions are worthwhile, and he has something to say about simple groups and how they've been glossed over in the study of semi-simple the algebras, which is interesting, and I don't think I've seen it said quite the way he says it in a lot of places. There's something worthwhile there, really worthwhile. I'll try to come back to, but I don't know. I was looking at different books I have, and I noticed most of the other books talk about the maximal tori, and that business much later, and he has it really, really early, and I don't think it's impossible to understand. I just think it's I don't know. I want to talk about sort of more basic stuff before I get back to that. Let's just say, okay, so and so I just bought you guys to my wife a copy of this, which is sorry, Lie groups, Lie algebras, and representations in elementary, and introduction, elementary. So don't pay attention to this. Introduction, and I don't know, undergraduate, graduate, whatever. It's a very careful book. We'll benefit from it. I think you guys will enjoy. And it's got pictures. See?
Ooh.
Colored pictures too. Yeah.
Is that a 4-dimensional picture?
Is it a 4-dimensional pictures? Yes. Every 2-dimensional picture is a 4-dimensional picture. It's just a boring one.
I guess we live in a boring world.
Well, you just have to remember there's 2 dimensions coming up off this page. One this way and one this way. So.
One this way.
Or no, it's one. I should say it's one this way, and then the other one is it's where we can't see it, right?
That's cool.
Go through the wormhole and shake our own hand or whatever. Oh no! Spoiler alert. Sorry.
Sometimes to help with your imagination, you just stop imagining and then wait till a little bit later to try to imagine.
This should help with your project though, because the latter part of this book is representation theory.
Yay.
And as I talk to students who've gone on from here, one thing that always comes up again and again and again is representation theory, and I think it would do us well to invest a little bit of our energy in that. So anyway, with that cop out being made, let us now ignore Stillwell and start again. Okay, so what is a Lie group? So let's start from the beginning. So let me just be a little bit informal. G is a Lie group means what? G is a manifold in the real sense. So that means that so in other words, I'm insisting there's some atlas of charts which covers G, all right, which makes it in local one-to-one correspondence with Rn. So I don't want to get into the details of that. It doesn't really matter too much to us, all that stuff. I will talk about that in the other days of the week here eventually. But anyway, so G is a manifold. And then also we have G is a group. Sorry. G is a group. And so meaning if it's a group, that means there's a couple things about it. One is you got multiplication. The other is you got inversion. Right, so the multiplication is a mapping from G cross G back into G again, and inversion is just a map from G to G, right? So in particular, you have something like G comma H, right? Maps to GH. And here we have G maps to, what do we call it, G inverse, right? Now, for this to be a Lie group, we insist that M and the inverse map are smooth. In the sense of manifold maps. Okay. So that, I mean, that there's some. I guess I have to talk a little bit about manifold theory here to make for you to understand what that is. I don't really want to get too much into it. Basically, the deal is if G is a manifold, then the Cartesian product of G and G is also a manifold with respect to what's called the product manifold structure. The topology is that of the product of the two manifolds, and well, like I said, I don't want to get into it. I'm sorry.
Is being smooth like in any way analogous to being differentiable in like count lines?
Right, like smooth. When I say smooth, I just really mean you can take as many derivatives as you want. Now, again, G here is an abstract manifold, so all right, fine details just for a second here. So G looks something like this, right? You pick a point. There has to exist some chart around it U. Okay, some domain around it U which contains P. From that P, there's this mapping. I'm going to call it psi. All right, and psi is a mapping down to Rn. N is the dimension of the group as a manifold. So to say G is a manifold means that locally it looks like Rn. Okay. Now, then, if you look at a function, all right, from the group, say a real valued function from the group, you can talk about a function like this, f. So it goes from the group over here to some real line. You say, well, what does it mean for a function from the manifold to the reals to be smooth? What does that mean? To say that this is a smooth function, so f is an element of smooth functions at the point P of the group. What that means is basically the only thing it can mean. It's smooth in the sense of advanced calculus, in the sense that down here, this local coordinate representative, this guy, is smooth. This guy, now this is a bijection, by the way, and essentially by definition is smooth. So let's see here. To go from here to here, I do what? I do F composed of what?
Psi.
I think it's going to be psi inverse, though.
Oh, psi inverse.
Right. Now, if you're thinking psi, you're thinking patches.
Right.
In differential geometry, we study parameterizations of spaces, so we go from the parameter space up to the manifold. But in manifold theory proper, we tend to look at coordinate charts. That's what this is. But this right here, okay, is a mapping something like from Rn to R again, right? So to say that this is smooth, that has a meaning which we've already talked about in advanced calculus. Okay, so that's what it means to have a smooth function on a manifold, a real valued function. Then you could talk about something like this. M is not a mapping from G to the reals, right? M is a mapping, M multiplication is mapping from G cross G to the reals. So there, what you would have to look at is something like, here's a picture of G cross G. Here's a picture of G. M goes from here to here. And if you pick a point, which would be like A comma B, then you're going to map down here to R2N. I'm giving you way too much detail about this stuff, I'm sorry. And this would be, what you do is you just take the Cartesian product of the coordinate map and the coordinate map, where this coordinate map, you just Cartesian product them together, and that gives you a 2n tuple rather than an n tuple. And then over here you still have this, and then you got Rn. And then to say that M is smooth is to say that every local coordinate representative of it is smooth. And that would mean this guy down here, which would actually be something like
compose with M.
Oh yes, thank you. Psi composed with M, composed with
Psi cross psi inverse.
yeah. And the inverse of psi cross psi is actually psi inverse cross psi inverse. So you can. It's not hard to figure that out. And this, of course, would be mapping from R2n to Rn. And to say that that's smooth, that means that it has a Jacobian matrix whose entries are all smooth functions. Now you could talk about like once differentiable or twice differentiable if you wanted to, and you could talk about like a C1 manifold or a C2 manifold or whatever. You could talk about a manifold where the local coordinate representatives were analytic or other things. Basically the structure is built into the manifold by the local coordinate representatives, whatever those those possess, the manifold possesses. Anyway, like I said, I've gone into far too much detail here. Sorry about that. Because we're not really going to be working with an abstract manifold. Even this elementary introduction, right? Elementary, just does matrix groups. So matrix groups are really nice because we don't quite need all this sophistication. But well, as he points out, the really nice thing about matrix groups is basically we don't need atlases because there's a global atlas we can use, which is just the atlas on Rn squared. The usual matrix norm gives us a way of measuring questions of topology and differentiability. But at the same time, it's a rich enough structure that if you can prove a theorem that connects Lie algebras and Lie groups, the various interesting theorems which connect these two worlds, the ones we can prove in the matrix case turn out to still be true in the more general construction, which is done at this level of abstraction, genuinely abstract manifolds. But that said, the beautiful thing about what we're going to do is this selling point I had for this course, which is you don't need manifold theory to understand it. You just need you need to be willing to look at matrix calculations and maybe do a little matrix analysis. So that's where I want to go. Let me erase this before you ask me a technical question about it, which I don't want to answer. I do want to get back to these things at some point with you guys, but not here now. It's just, a good slogan for a Lie group is it's a group where you can do calculus. That's what it is. And, I was talking to somebody yesterday, and they said, you should emphasize that a Lie group is not first a manifold. Oops. It's first a group. The group structure is what makes it so special. Now, a matrix Lie group. Right, a matrix Lie group is really what we're studying. So a matrix Lie group is a subset of what? Let's see here.
The general linear group and all that.
It's a subset of GLN, but GLN what? Definition 1.1. Sorry, it feels good. The general linear group over the real numbers is GLNR. Some of this is going to be review, sorry. The general linear group over the complex numbers is GLNC. Okay. So the general linear groups are indeed groups with respect to the operation of matrix multiplication, right? And inversion. And we're not quite to the definition of matrix Lie group just yet. This is the general linear group over R, the general linear group over C, right? Definition 1.2. So this is the other notation for matrices, which I don't tend to use, but I probably should. M sub n C. People who use this definition for matrix don't like what I write. This is what I usually write as Cn by n. Whatever. Those are the same animal.
So
Yet other people will write.
need.
Yet other people will write this mat and C or something like that.
They don't bother to assert that it's square it's just assumed?
Yeah, square, because well, we're going to look at the, we want to be able to, we were looking for a group, so we want to be able to like multiply two of them and get another one back, so if they're
Yeah,
rectangular, it would take more imagination.
that would be very.
Shut up. Oh. No, I shouldn't say that. It wasn't even anything political, so you're, it's nothing to say. 1.3.
That was the definition for 1.2?
Yeah, just that's notation. That's the space of all n by n matrices with complex entries. Right. Let's talk about a sequence of complex matrices. We say that, so a sequence of complex matrices is what? If you have A, right, a mapping from the natural numbers to Mn. Well, that doesn't sound good. I do worry working here sometimes. Like, do they really know how to build buildings that well?
Whoops, the bowling alley is going to be in your office. Sorry.
That'd be quite the earthquake. Anyway, this is a sequence, okay? And then he says, we say AM converges, he says the sequence A sub M converges to A, all right? If and only, no, if each entry in AM converges to the corresponding entry, right? So, in other words, he's saying that that means that the limit as n goes to infinity of A sub M, right, is equal to A if the limit as m goes to infinity of A sub M sub ij, right, is equal to aij for all ij. Okay. Make sense?
Is that a... Oh, that's just a definition.
Yeah. It's not I don't think that's a necessary definition. You could define, certainly you can define convergence of matrix sequences and derive this as a consequence. I mean, this is the vector limit theorem in my advanced calculus course. It's,
Well, I was just going to ask if it should be if or only if, but I realized it's just a definition.
he says it's a definition, yeah. No. Sorry. Definition 1.4. By the way, this is Lie Groups, the Algebras and Representations, an Elementary Introduction by Brian C. Hall. So, where was I? What is a matrix Lie group? A matrix Lie group is any subgroup G of GL and C. Now one of the things this book is going to do, which is going to be clarifying, is he's not going to do any of this monkey business with quaternions. Quaternions are great and all, but they just, come on, there's certain ambiguities in the notation, which is just vexing and annoying. And push comes to shove, still does stuff with complex numbers. So we've got this like extra notation, which is conceptually useful, right? But right up until the point you try to do a problem, at which point you're like, but is a quaternion a quaternion, or is it 2 by 2 complex number?
Well, the only useful group we got through with quaternions was the abstraction of the rotation group on them.
Oh, the SPN. I mean, don't get me wrong, I think quaternions are awesome and interesting, but I want something more specific for you guys to work problems in. Okay, so, where were we? Let's see here. Any subgroup G of GL and C with the following property. Aha. Such that what? If AM is any sequence of matrices in G, and AM converges to some matrix A, then either A is an element of G or A is not invertible. So, if A sub M is an element of G for all M in N, and the limit as M goes to infinity of A sub N is equal to A, right? Then what? two cases. Either,
A is an element of G.
right, or,
A is not an element of GL and C.
very good. At which point you should be like, hey, that's what Stillwell said, right? Because he said that a matrix Lie group was going to be one that was closed under non-singular limits, which is what this says.
I like this one better.
The condition, I mean, it's not fair to Stillwell. This is the second, every time, the second book you read on anything always seems better.
I guess that's true.
But anyway, I digress. I do love Stillwell's writing. The condition on G amounts to saying that G is a closed subset of GL and C. He says this does not necessarily mean that G is closed in here. It's closed inside the general linear group. What's that mean? Okay, that's a kind of a question for the topology course, okay? Yeah, that's a topological comment. Topologically close. Of course, G is closed in the sense of a group. I mean, it's a group. So when we talk about a subgroup being closed, we're saying in the topological sense. So what would it mean? So let's just say, I mean, this is
all of its limit points in G, L, and C are also going to be in G, which means that its closure is just going to be itself. And but in M and C, all of its limit points aren't necessarily going to be in G, so it's not closed.
I see. That makes sense.
Okay, the closure.
Right, so G is equal to its if you tack on all the limit points, the limit points are the points which, well, you probably know this better than I do at the moment you're taking real analysis, right?
Yeah.
So the accumulation points of G, the points which sequences accumulate to, put those all on G. That's the closure of G. The question is, where are you allowed to take those points from, right? So.
So we're saying G is closed under limit points. Is that
Closed in.
I mean, closed means it includes its limit points.
So G closure is equal to G. Now, yeah. Although I probably should just say closure, because we're not going to talk about closure that much. Whereas I may want to use that G bar for something else. All right. He says, the condition that G be a closed subgroup, as opposed to merely a subgroup, should be regarded as a technicality, in that most of the interesting subgroups of GLNC have this property. Most of the matrix Lie groups G we will consider have the stronger property, in fact, that if AM is any sequence of matrices in G and AM converges to some matrix A, then in fact A is in G. In other words, most of the matrix groups that we consider are actually closed inside the larger set of possibly non-invertible matrices. All right. And then he starts listing examples. Maybe a counterexample will be nice, though, huh? So here's this counterexample. An example of a subgroup of I gotta get this eraser dust on my fingers, then I'm getting on this book. It hurts me. I love this. This book is so pretty. I hate to mar it with this disgusting. If I had a chalkboard, I wouldn't have this problem. I need a chalkboard. For the sake of my books.
Oh, yeah.
Yes, for the books. Let's see here. I digress. Any subgroup, an example of a subgroup GLLC which is not closed and hence is not a matrix Lie group. He says, look at the set of all n by n invertible matrices whose entries are real and rational. Ooh, that's an interesting. So let G equal to A, an element of G, L, and C, all right? Such that A is an element of MNR, I suppose. Oh, it's worse than that. It's even worse than that, isn't it? What did I just say? Real and rational. Ooh.
So cute.
Yeah, trade that R for a Q. Ooh. That's kind of neat, right? If you think about the set of invertible matrices with rational entries, is that closed under inversion? So you think about the thing is we have that formula for the inverse of the matrix in terms of the classical adjoint.
Yeah.
The cofactor thing. Think about it. It's just formed from selecting certain submatrices, calculating their determinants, and dividing by something which is non-zero.
Right.
Put rational numbers into that formula,
Get them out.
get rational numbers back out. So the inverse of an invertible matrix with rational coefficients is once more invertible with rational entries. I mean, that is in fact a group. But then what? He says, but you can easily have a sequence of invertible matrices with rational entries converging to an invertible matrix with some irrational entries. He says, in fact, every real invertible matrix is the limit of some sequence of invertible matrix with rational entries. In other words,
Really?
that is dense up in here.
We know that too.
You guys know this stuff for real numbers, not for matrices.
Right.
we have, it is at a slightly different, I mean, but as much as it's different, the song remains the same. I mean, the counterexample you can get from, here, look at n equals 1. I mean, if you want a specific counterexample, look at the stupid n equals 1 case, and let your sequence be an equals to 1, 1.4, 1.41, 1.414, and so forth. Just the decimal.
We use that all the time, right?
Decimal. Oh yeah, decimal. I did that in Calc 2 this semester. That's funny. I didn't even talk to Dr. Morris about it. I just think it's a natural example, right? This, of course, goes to the square root of 2. Every non-zero, right? Every non-zero complex number is invertible, and so here you have a sequence of invertible, rational, 1-by-1 matrices, which is in fact converging to something which is.
So that makes it not a matrix subgroup. Is that what you?
Well, the point is
This
that.
a subgroup. It's just
The
not-
matrix leader.
it's not like-
Right, the point is this converges to that,
Mm-hmm.
and this is neither, what is it? It's neither an element of G or not an element. I mean, the point is it does converge, and it's not something in the rational.
Right. So it's not in G and it's not in the rational.
Right, it's not in G, and it is in fact in here.
Yeah.
Oh, okay.
And I suppose you can come up with kind of similar silly examples. 2 by 2, you can use the same, you just piggyback on this example.
Square root times I. Yeah.
I could do like this, right?
Ooh.
It's just this it's like this example all the way down. I mean, I don't know, there's of course other less contrived examples you could come up with.
So that's a really cool dense matrix.
There are very beautiful arguments that can be made for rational matrices sometimes, that then the fact that rational matrices are dense in the complex matrices gives you a way of proving certain things which are like not at all obvious. I'd like to show you that theorem I'm thinking of. I don't remember what it is right off the top of my head though. Oh, what's he doing here? Oh, he's got something cool. Oh, how would you know?
I thought you were talking to yourself.
It was. But not in a good way. Let's see here. E to the IT. He does this. E to the IT 0, 0, e to the ITA, such that t is a real number. And what's the deal with a? he says let A be an irrational real number. A be an element of R minus Q. Let's see here, why is that not a... It's not the same example anymore, of course.
So A is irrational.
So this is the proposed...
It's also not a Lie group.
So, by the way, this is essentially...
This wouldn't be closed under multiplication, would it? Or,
Yeah, I mean, I think so. If I take the product of these two things, I get
Yeah.
like e to the t1 plus t2, e to the I,
yeah.
t1a plus t2a. I mean, it's t1 plus t2 times a. It is a group. It's the topology that's screwy. Geometrically, this thing is really interesting. So A being irrational means that if you take the limit, you know, like it never gets back to where it started again. If I was to take, oh man, how can I say this? I guess I could take something like A sub n equal to, gee, I don't know, e to the I. I can't even think what to put here. Maybe just m. Something like that. And of course you could make it more fun here. You could divide by something, so it would take longer for it to get back where it started. But you know, if I do like say here, I'll just make it interesting. Divide it by 2. So if you n equals 1, n equals 2. I need a pi, don't I? Otherwise, it's still not interesting. Let's see here. I n pi, right? I n pi a over 2. Something like that. So when I take n equals 1, 2, 3, when I get to 4, I'm back where I maybe back to like when I get to 5, I'm back where I started, if you start at 1. But over here, I can never go back. If I could go back, it would say that A is rational. If I had that e to the I and pi a over 2 was equal to e to the I, say m pi a over 2 for some m and n, then what that would mean is that n pi a over 2 is equal to m pi a over 2 plus 2 pi k for some integer, the 2 pi periodicity of the imaginary exponential, and then divide the pi's, and what do you got? You got like n minus m times a is equal to k. See, the product, the difference of two integers times an irrational number is equal to an integer again. That's pretty good. That's a pretty sneaky deal right there. You can't do it, right? What this is, right? And so I'm trying to think how that shows. How does this sequence contradict this stuff up here? Can you see it already?
So the limit.
Well, that sequence doesn't even converge, does it?
No, this one doesn't.
Right. So I think we need to find one that does converge.
but I guess what you can do is just take something like this. Well, it still seems like A would be in GLNC.
Right, but don't we want it to be in GLNC and then not an element of G? Isn't that? And that it converges to something that's not in.
Oh, right. Yes, I got it turned around. I think we can pick one here, right? That through playing with this, kind of like that idea, will converge to, like,
Because if we make it periodic like that, it'll never converge.
there must be a way of taking something in here so that it converges to something that's just with not of this form, and yet still in GLNC. That's what has to be the point. I don't know what that is, right? It's probably in here if I just open it back up again. The reason I think it's interesting, though, is geometrically what's going on. You know what this is? This is a torus. It's T2. So this is like a circle. That's like a circle, basically, in C2. And you could kind of like picture it something like this. Well, it's not a torus, though, is it? I mean, it's dancing around this. It's on this torus. It's not the whole torus, though, right? Because you're only picking up these kinds of things, not.
If we took the A away, would it be?
If we allow for arbitrary arguments here.
Like if the A's don't have to be the same?
Should it matter if the A is there or not? I don't understand this example well enough.
The A is fixed, right? Or is it not
Yeah,
fixed?
A is fixed, I believe. That's a good question. Is A fixed here? I thought A was fixed.
I would assume it was.
That's what I thought.
Yeah, I think so.
But, so like, you could think of this one's kind of like going like that, right? And this one you could think of as going the other way, graphically. And so this is something like it's going round and round and round, But when it gets back, it doesn't go where it was before. It keeps going, and so like it's going to densely wind around this torus, I think.
And it would never get back.
Right, but it never gets back where it starts. But
That was interesting.
that sort of thing causes trouble for basically the topology, which we want we don't want this kind of example is the thing. It might have a group structure, but its topological features are not desirable for what we are doing with topology. I'm sorry, I digress. I should read more. Right after my thing. Okay, so what are our examples? Now I've almost showed you a non-example. I mean, I've invited you to try to understand why this is a non-example. All right, that'll have to do.
It kind of helped.
I think we succeeded in the other one, but. Okay, so basically our typical example's G, right? What are they? Well, of course we've got the whole thing, the whole kit and caboodle, right? Like the GL and R. Well, that's one. It's like the universal group. It's just kind of like everything there, or the same for C. But I should caution you, we're thinking of them, ultimately we're thinking of them as real manifolds. That you'll see more clearly in a bit, but there's also ON, right? We talked about that a little bit. It's A such that A trans, oh man, I'm gonna leave myself enough room. So A in Rn by n such that A transpose A equals to I, right? Then there's SON, right? A such that, well, what did you say? ON intersect what? SLNR. Where SLNR is what? A in n by n reals such that what? Curses. Apparently I don't know how to make a table. Alright. Man, this marker's faint. I can find a different one. Do we have any other examples that we're interested in? Surely we do, right? Yeah, UN. So UN is what? UN. So we want a n by n complex, right? Such that a dagger A is equal to I, right? And let's see here, of course SUN, also popular, which we'll say is A, is, good gracious, UN intersect what? SLNC. So here SLNC is, come on, this is bad marker day. There where it belongs. Keep not throwing it out, and then it comes back and wastes my time again. See here. So SLN is just what it sounds like. That is the inverse image. Oh, curses. Fine. A n c n by n, such that the determinant of A is 1. All right, all of these definitions we made before. There's also the symplectic one, which is captured in terms of a J matrix. Let me write that over here, since I now have an explicit formulation for it. I'll tell you in a second. Come on, where'd you go? All right. So you let he says, well, I'll tell you what, I'll start at his starting point. He says, consider the skew-symmetric bilinear form B. It's a mapping from R2N, okay, bilinear form, right? So it's from R2N cross R2N to the reals, right? And it's defined as follows. B, its notation, B of xy is equal to sum, k equals 1 to n, of xk, yn plus k, minus xn plus k, yk. It's clear that this is a bilinear form, right? I mean, if you put x1 plus cx2, clearly you'd get c bx1 comma y plus bx2 comma y. So like the fact that it's a bilinear form in the sense we talked about in advanced calculus should be fairly clear from this formula. And here's what he says. The set of all 2n by 2n matrices A which preserve A. So definition, SP, the symplectic real order n matrices like this, SPn semicolon R is, it's going to be a subgroup of GL2NR, all right? And in particular it is A in R2n by 2n such that you could just as well put GL2n here in the place of that if you wanted, okay? You could replace that with GL2NR without loss of generality, okay? I'm not saying that is that, I'm just saying you could do that, okay? I should probably just do that. All right, too late. Then it's those that it preserves B. Okay, so like B of AX AY is just equal to BXY for all X and Y in Rn.
Back to it.
Mm-hmm.
X and Y are separately in Rn. Oh, yes. You're right. I'm sorry. My bad. Yep. Okay.
So we're basically saying it's like, you know, isometry, if we can use that.
Yeah, it's like an isometry, except that I mean the danger, of course, in saying that is it's not really a metric exactly. I mean, this is a kind of funny thing. It's not symmetric, right?
Yeah.
But it's not far from that either.
Like kind of a distance.
Yeah. So here's the kind of sorta right. He's like you could write B this way. You could say B of XY is equal to. You could write it this way. It's X comma JY. Right, where the bracket there is just the standard Euclidean inner product, where like VW is V transpose W, you know, the usual Euclidean dot product. Now this J, right, what is J? Well, J is this 0, I, minus I, 0. That's a 2n by 2n matrix. So, fun exercise, like totally enjoyable exercise, won't take you long. You can show that this implies, in fact, that A in SPN actually is a solution to has what? It's going to have, you know, so make sure I get it right. Oh, what's that notation mean? It's got this TR. It's TR. Oh, transpose. he's just doofus. Like, what's TR? It's TR. A transpose JA is equal to
Fragile.
Fragile. What's that from?
Christmas story.
Christmas Story. Ah. Oh man, I should know that. Disappointed in myself. So that's the condition. Isn't that striking? Just like, remember when we studied Lorentz transformations before, we had like lambda transpose eta lambda equals to eta, or if you replace J with equal to I, if you put J equals to I, you get the orthogonal, so that's this one, right? Just use your imagination, you can see there's an I here. If you replace that with other things, you get the Lorentz matrix, the Lorentz matrices and other things. Yeah.
Why did we define J the way we did then? If it works with I for the ON and UN.
See, another way we could have said the XY is actually equal to this. It's actually X transpose JY. It's totally equivalent. And then so, like, if I say B, oh man, I think I'm doing your exercise for you.
Well, I mean, you said the Euclidean metric, which is...
My point is, this is the formula for such a bilinear form. Set aside J being this specific thing. If J is any matrix, in fact, okay, could be this one, could be any number of things, and this same calculation goes through. See? So like J equals to the identity matrix gives you ON. If you have J equals to this guy, -1, 1, 1, 1, all the way down, you get what's called O. I think he calls this one, he has this in his list of examples. O. Come on. Here you go. O ON1, I believe. Which is basically like saying it's almost orthogonal. In particular, if you look at the case O41, O41 includes Lorentz transformations. The kind that are
Which would be
physically
the
interesting.
The first four are negative one, and everything after that.
Mm-hmm. Yeah, this J becomes the eta I talk about in other places. Interestingly enough, if you look at O41, this is an example of a Lie group with 4 connected components. O, on the other hand, O just has 2 connected components like we talked about before. Okay, but hey, I'm pretty excited about this because now we have a rather explicit characterization of what SPN is. See, it's this. That is what it is. And what is SPN? What's SPNC then? I mean, it's up for grabs, right? But what he says is, well, you can define the bilinear form on C2n by the same formula, this one. Just let x and y be 2n complex. Let x and y be from C to n. Same formula.
With the Hermitian product.
And I guess that is the question. Is it the Hermitian product, or he says this involves no complex conjugates.
Maybe not.
Hmm.
Well, that's nice.
He says, oh well. Here he gets to the point. Here he's like a.
What was the right column of that supposed to be?
Oh, we're getting there.
Oh.
Don't worry, I'm not done yet. A element of SP, comma, NC means what? He says that means A, if and only if A transpose J, A is equal to J again. He's like, note, this involves A transpose, not A conjugate. In fact, determinant of A is equal to 1 for all A in this. Oh, and then one other thing. There's yet another SPN thing to talk about. There's the so-called compact. This is the okay. So language. This is the complex symplectic group. A complex symplectic group. Of course, this you might have guessed is the real symplectic group, right? And then he has one other he calls the compact symplectic group is defined to be SPN, no N or C. That's defined to be the complex symplectic group. Okay. Intersected with what? He has more examples I'm going to save for next time, by the way. I don't want to just do an example today. I want to show you something new. So that it's intersected with U, the unitary. What size should they be then?
SPNC is R4n by 4n, right? So every element A is in C, C2n by 2n.
I think it would be the subset of GL 2NC, is that right? Or is it 4N or is it 2N? It's curses, why did I put that away?
I think it would be 4n if it was R.
Both of it, I think it's 2NC.
Yeah.
Okay. I should have put a bookmark in this thing. What's wrong with me?
Because J is also 2n by 2n. and whatever it is.
Oh yeah, I was right. It's 2n by 2n complex. So, and that's U2n. Yeah. All right. So I'm excited. At least we have some more. Yeah, but I mean, I prefer this description. I think this was in the exercises in Stillwell. I just think it's good for us to talk about. Okay. So this list is incomplete, of course, right? There's more. Now, over here we can talk about the so-called Lie algebra. All right. And one of our main goals this semester, right, in this class is to understand the connection between this Lie group and this Lie algebra, to study the structure of both sides, to understand how it's related. And so I guess the first question is, how do you define the Lie algebra? Now, personally, the way I've seen it defined before, okay, was that this was equal to the tangent space at the identity of the Lie group. Okay, that's what in my previous coursework, that's what I've seen. Hall, though, he defines it. He says it's the, I'm with races. He says, disturbing. He says it's the set of exponentials. He's like, it's just matrix exponentials of oh, I'm not saying it right. He says it's sneaky. He says it's very sneaky. Very sneaky and good. Sneaky in a good way. By the way, I'm not quite following Hall either. And that's partly because we've already done stuff and I don't want to just redo everything. So I'm actually now in his chapter 2. And I'm skipping over the part where he defined the matrix exponential. Okay. And the matrix logarithm. And the properties matrix exponential. Okay, here we go. Page 39 of Hall. It is a G be a matrix Lie group. The Lie algebra of G, denoted frac G, like so, is the set of all matrices X. Ooh, it's very sneaky. Now, we can put a question mark as to whether or not these are equal. Certainly, whatever is meant here, there's some kind of convention, right? It's the set of all matrices X. Okay. Well, I'll just say X, such that e to the tx is an element of G for all real t.
What is X?
Matrix.
Just a matrix.
A matrix. Now I think that this is either going to be taken from GL and R, okay, or GL and C, depending on the group we're looking at. But we're always looking at real parameter here. This is always T. It's not like T one place and C the other. It's just T. And that's why I say that we're really looking at Lie groups as real manifolds. That's part of it. That is sneaky. Okay, so obviously this begs the question, how do you define the matrix exponential, right? Now, I have asked and answered that question in other courses you guys have taken, right? So this is in our first day at the fair on that question. Whatever that means. I never go to a fair, I don't really know. I shouldn't even use that saying, I don't have life experience. You know? I don't have proper life experience to use that saying. Like, do I have to talk about fairs? But this is the definition, right? E to the A is equal to the sum. N equals 0 to infinity of a to the n over n factorial. Right? And you can prove that this series converges